Okay, hello everyone, and welcome to this fluid mechanics tutorial video. Today we're going to be doing problem 5.95, and it says, when gauge A indicates a pressure of 130 kPa gauge, then cavitation starts to occur in the venturi meter. If capital D equals 50 centimeters and D equals 10 centimeters, what is the water discharge in the system for this condition of incipient cavitation? The atmospheric pressure is 100 kPa absolute, and the water temperature is 10 degrees Celsius. Neglect gravitational effects. So what are we looking for in this problem? Well, this problem is asking us for the water discharge in the system for this condition of incipient cavitation. So we're looking for Q. So Q equals what? To do this, we are going to want to use the Bernoulli equation. So Bernoulli equation is just pressure 0.1 over gamma plus its elevation plus its velocity squared over 2g equals the pressure at another point, let's call that 0.2 over gamma, plus its elevation plus its velocity squared over 2g. So while the Bernoulli equation does not include Q directly, we can manipulate V1 squared to include Q. So we know Q equals VA. So let me write that. Q equals VA. Therefore, V equals Q over A. And we know V squared just equals Q squared over A squared. Okay. So it's important to note that the water discharge in the system is just the same throughout the whole tube. That's because of the continuity equation and just because of the conservation of mass. So let's rewrite this Bernoulli equation. So P1 over gamma plus its elevation plus V1 squared over 2g. So you write V1 squared as Q squared over A squared, like that. So Q squared over A squared. So it's important to note here that the area at point 1, actually it's important to know, I should have mentioned that. Let's put our points here underneath the indicator and one at the venturi meter, like this. Apologies for that, that would have been more clear, but it's important, at least we have it now. So at point 1, the area is different between the cross-sectional area at point 2. So therefore we are going to write it as A1 squared over 2g. Remember to include that 2g from the original Bernoulli equation. Okay, so let's rewrite the second half of this equation. Okay, Q again is going to be the same for both sides because it's constant. The areas are going to be different because the diameters are different over 2g. And if we're smart with this, we'll put our points along this line, meaning the elevation of our points will be the same. So Z1 and Z2 are the same, so they cancel out. Okay, now we want to solve for Q. So let's move all the Q terms to one side. So we're going to do P1 over gamma minus P2 gamma, so they're on the same side, equals Q squared over A2 squared over 2g minus Q squared over A1 squared over 2g. Here, and we can rewrite that as Q squared over 1 minus 1 A2 squared 2g minus 1 over A1 squared over 2g. And so we can simply find Q by dividing P1 minus P2 over gamma. Divide that by 1 over A2 squared over 2g minus 1 over A1 squared over 2g, and taking the square root of that. This might look complicated, but it's a pretty simple calculation. Okay, so that's our final equation for Q. So what are our unknowns for this equation? We need to figure out P1 and P2. We also need to find A2 and A1. We also need to find gamma and G. Okay, so let's look back at our problem statement, see if we can find these pressures and areas. Okay, let's find P1 first. So in the problem statement, it actually tells us the pressure at our point 1, which is this, our point where A is, basically. So in the problem statement, it tells us the gauge tells us that it's 130 kPa gauge. 30 kPa, lowercase k, gauge. And it's important to note that it's gauge pressure, not absolute pressure. Okay, to find pressure 2, it's a little more complicated, but pretty easy to find. One important thing to note about this problem is that it's under the condition of incipient cavitation. Therefore, to have cavitation, the pressure at that point needs to equal the vapor pressure at that temperature. So we know the water temperature is 10 degrees Celsius. So we can just look at this chart over here. And we know the vapor pressure of water at 10 degrees Celsius equals 1,230 newtons over meter squared absolute. So we need to write that down. Okay, side note, newtons over meter squared just equals pascals. Okay, one other important thing to note is that that chart gave us pressure in absolute, not gauge. In order to use these pressures in the Bernoulli equation together, they both either have to be in absolute or gauge. So it will be easier to convert the pressure 1 gauge into absolute, because that's just the pressure gauge plus the pressure atmospheric. And the atmospheric pressure is given to us in the problem statement right here, 100 kPa absolute. Okay, so P1 absolute is actually 130 kPa plus 100 kPa, which equals 230 kPa absolute. Now we have both of our pressures in absolute. Now let's look at the cross-sectional areas. We know the cross-sectional area for a tube is as a circle, and we know the equation for a circle is this pi diameter squared over 4. So let's look at point 1 first. So we know that the area for point 1 is pi times capital D squared over 4. Let's write that down. And similarly, we know point 2 is this pi times little d squared over 4. And we are given big D and little d. So let's actually just replace the numbers in there. So big D is 50 centimeters, and we need that in meters to use in the Bernoulli equation. So that's 0.5, and that's 0.1. So Microsoft OneNote's actually nice and actually solves it for us. And in the equation that we want to solve below, we actually need A2 squared and A1 squared. So let's just solve these for squared now. And now we simply get those for the squared values of the areas. Okay. So we also need G and gamma. And G is acceleration due to gravity, so that's 9.81. And gamma is a specific weight. So I'm going to write gamma actually. That equals 9,810 for a temperature of 10 degrees Celsius. So now we have all that we need to solve this problem. Let me move this down. We simply just plug in now. Okay, so after plugging in all these numbers that we have, we get this equation. After simplifying that, we get square root of 23.32 over 824.9468. And after solving that, we get Q equals 0.168 meters cubed over seconds. So that is all for this problem. If you have any problems, you can leave them in the comments and I'll try to answer them. And please leave a like if this was helpful. And have a great day. Bye, y'all.